Okay, so now we're going to look at another property of liquids, and that is known as surface tension. Now, what is surface tension? Well, surface tension is the resistance of a liquid to an increase in its surface area. And this is as a result of several things happening at the same time. In the first place, what you'll have is that you're going to have attraction between the molecules at the surface of the liquid and the molecules below the surface of the liquids. And what you'll find is that the attraction of the two results in the molecules at the surface of the liquid being pulled below the surface layer. And if you take a drop of liquid, for example water, what you'll find is that it automatically forms a sort of spherical shape. Again, that is due to surface tension, where the molecules on the inside of that droplet will pull the surface molecules towards the center, and therefore as a result you end up with a droplet. Substances with large attractions between the molecules, they typically have high surface tensions. Another property exhibited by liquids is what is known as capillary action. And capillary action is basically the spontaneous rising of a liquid in a narrow tube. And this has to do with some forces that exist, in this case, between the liquid and the surface of the tube. Typically the tube is made of glass, and what you'll find is that there's some attractive force that exists between the liquid and the walls made of glass in the tube. So there are two types of forces in this regard. We have what are known as cohesive forces that exist within the liquid, and then we have adhesive forces that exist between the liquid and the walls. And if you have the adhesive forces being greater than the cohesive forces, then what will happen is that the liquid will start climbing the walls of the capillary tube. So as stated here, when you have the liquid placed in a cylindrical glass container, then you're going to have what is known as the curved surface of the liquid, which is known as the meniscus. And this diagram shows you basically the shape that results when you have the adhesive forces being greater than the cohesive forces between the water molecule. All right. Now, so pretty much all liquids behave this way excepting one, and that is mercury. And mercury is the opposite in terms of the fact that the cohesive molecules or the cohesive forces between the mercury ions that are present in the mercury metal would be greater than that of the adhesive forces. So if you look at mercury in a tube, what you'll find is that the surface will not curve down as we see here, but will curve upward. All right. Okay, so that's as far as that is concerned. So the next property we're going to look at here is boiling point. And the boiling point, by definition, is the temperature at which the vapor pressure of the liquid is equal to the external pressure above the liquid. All right, so that's what we call the boiling point. Now, the normal boiling point is basically the temperature as stated here, but the atmospheric pressure would be 1 atmosphere. All right, and if we look at the table that we saw earlier in the previous video, you'll see that for different liquids, as I said before, they have different vapor pressures at the same temperature, right? Now, if the vapor pressure is 1 atmosphere, which is the same thing as 760 torr, then the temperature will be equal to the boiling point, because remember, 1 atmosphere is the atmospheric pressure, and if the vapor pressure of the liquid is equal to 1 atmosphere, then the boiling point at that temperature, or the temperature at that point, is known as boiling point. All right. So water boils at this temperature, 100 degrees Celsius, because that's where the vapor pressure is equal to the atmospheric pressure. All right. And as you can see, we have different substances here, and the boiling points of these substances are shown. And you see here that water has a significantly higher boiling point than the other substances labeled here. There's some other information here which I won't get into right now. We're going to talk about them later on. Okay, so as you can see here, the normal boiling points for these substances are given, and these can be plotted on a curve of vapor pressure versus temperature. And based on that curve, we can determine the boiling point of a liquid if we do such a plot. So here is a graph which shows you the plot of the three substances we showed you before: ethyl ether, ethyl alcohol, and water. So this is a plot of vapor pressure versus temperature for water. This is a plot of the same thing for ethyl alcohol, and the black line here is for ethyl ether. Now remember, the vapor pressure must be equal to the atmospheric pressure for the substance to achieve its boiling point. So remember, the vapor pressure being equal to the atmospheric pressure would be, under normal conditions, 760, right? So the normal boiling point for ethyl ether we can get by drawing a line like this across from the 760 point right here on the y-axis, and where it hits the line, and you drop a vertical line down here where that cuts the x-axis, that would be the boiling point of that liquid. In the case of ether, by my estimation, that's about 34 degrees Celsius. In the case of ethyl alcohol, that's about 78 degrees Celsius. And of course, in the case of water, that's 100 degrees Celsius, right? So that's how you can determine the boiling points for different liquids if you make a plot of the vapor pressure of the liquid versus the temperature of that liquid. Okay, so that's showing you the boiling point of ethyl ether. It says here 34.6 is the boiling point here. In the case of ethyl alcohol, 78.4. And of course, in the case of water, that's 100 degrees Celsius. So using that, we can determine the boiling point of any liquid at any temperature if we have a plot for that liquid. So we could, for example, look for the boiling point of, let's say, ethyl alcohol when the external pressure is 500 degrees. So you draw a vertical line here, and then where it cuts the green line, you drop a vertical down here, and you get your boiling point, which is, well, this doesn't look correct. It says here, at 700, right? When you drop the line down here, it becomes 77 degrees, all right? Here, the boiling point would be about 60, looks like 67 degrees Celsius in the case of the boiling point of ethyl alcohol at 500 torr. But at 700 torr, the boiling point increases to 77 degrees, all right? Okay, so that's as far as boiling point is concerned. Let's talk about the freezing point or melting point of a liquid or of a substance. The definition of a freezing point is basically, well, the definition of freezing is when you have a liquid changing from or into a solid, and if it's going the other direction, then we call that melting. The temperature at which a solid melts is the same as the temperature at which the liquid of the same substance freezing. So therefore, the freezing point and the melting point are both the same thing. So at the melting point, you have this equilibrium taking place between the solid state and the liquid state, all right? Now, the freezing point of water is 0 degrees Celsius. So basically, once you get to that temperature, basically as you're cooling your substance, and then you get to that temperature, you have an equilibrium set up between the two. So it just continues. Whoops, I'm sorry, I jumped the gun a bit here. Let me go back and do this. So as one molecule of ice enters the liquid state, another molecule comes out of the liquid state into the solid state, and that continues. So you have that back and forth between the solid and the liquid state taking place. Okay, so let's talk about the changes of state. So I think we're all familiar with the different states of matter. You have the solid state, the liquid state, and the gaseous state. So what we have here is oftentimes referred to as a cooling curve. It shows you how the temperature changes as you add more and more heat to a substance, all right? So if we start with a substance here below the freezing point, so let's say we're talking about water, then we have solid ice, and as we heat it, the temperature increases until you get to the freezing point, which is 0 degrees Celsius. And as long as there's ice present, the temperature will remain. So even though you're heating it, the temperature will remain at 0 degrees Celsius until all the ice has been converted to liquid water. So when that happens, with the addition of more heat, the temperature will start to rise until you get to the boiling point of water. And the temperature will stay at the boiling point, which of course is 100 degrees Celsius. The temperature will stay at the boiling point as long as you have liquid present. But of course, what you're having as you add heat to this is that the liquid will be converted to vapor, or the water will be converted to steam. And that continues until all the water has been converted to steam, and therefore what happens after that is that the temperature starts to rise again, and the temperature will just simply continue to rise from there on forward. Alright, so that's basically what happens when you heat a substance starting from below the freezing point to above the boiling point. Okay, some definitions here. Heat of fusion. That, by definition, is the amount of heat needed to change 1 gram of a solid to its melting point into a liquid. So that's basically the heat of fusion. All right. So we could use, and by the way, let me go back to this table I showed you earlier. Let me scroll back here. Right. So this table gives you the heat of fusion of water, which is 335 joules per gram. So what that means is that for 1 gram of water, we need 335 grams to convert it from, if you have 1 gram of ice, you need 335 joules to convert that 1 gram of ice to liquid. All right. So that's what that means. And we can use that to do certain calculations, such as the example I was about to show you here. Let me see here. Okay, so the question says, how many joules is needed to convert 10.0 grams of ice at 100 or at 0.00 degrees Celsius to water at 20.0 degrees Celsius? So to do this problem, and let me go to the pen function here. Now I need to remind myself of what the heat of fusion of ice is. I'm sorry about that. Okay, so the heat of fusion of ice is 335 joules per gram. Okay, so let me go back to the question. Okay, so this is the question. How many joules of energy are needed to change 10.0 grams of ice at 0.00 degrees to water at 20.0 degrees Celsius? Okay, so the way I would set up this problem, go to the pen function here. The way I would set up this problem is that I'll look at the process in 2 steps. The first step is I have H2O solid at 0.00 degrees Celsius, and that is converted to H2O liquid at 0.00 degrees Celsius. All right, and this is where the heat of fusion comes in. Heat of fusion. All right. Then we look at the process of heating water from H2O liquid at 0 degrees Celsius to H2O liquid at 20.0 degrees Celsius. And at this point here, the specific heat of water will be involved in this calculation. Right? Now, the heat of fusion part will come into play because you have 10.0 grams of H2O, and we multiply that by the heat of fusion, which, as I said before, is 335 joules per gram. All right? And that would be equal to, let me do my, I think I can work this out in my head. This would be equal to 3,350 joules. All right? So that's the amount of heat involved here, right? Now for the specific heat part, the equation I would use is Q is equal to M times C times delta T. Now this equation should be familiar to you. We discussed this topic in chapter 10. So in this case, M is the mass, which is again 10.0 grams, times the specific heat, which of course is 4.184 joules per gram degree Celsius, times the temperature change. Now, what's the temperature change? The temperature change is 20.0 degrees Celsius minus 0.00 degrees Celsius, because remember we're going from 0.00 degrees Celsius to 20.0 degrees Celsius. So when I work that out, that's 20 times 4.184 times 10. Okay, the answer I got is 836. Okay, round off to 366, that would be 837. And this would be joules, all right? So this is the amount of heat that it needs to melt the ice, and this is the amount of heat that is needed to raise the temperature of liquid water from 0 degrees to 20 degrees. So basically total heat needed, do it up here, would be equal to 3350 joules plus 837 joules. And when I work that out, 3350 plus 837, the answer I get here is, when rounded off to the 10th place, would be 4190 joules. So this should be 1 right here. So this would be the answer right here, all right? So that's how we do a problem of this type. Okay, let's talk about the heat of vaporization. The energy required to change 1 gram of a liquid at its boiling point into a vapor is called the heat of vaporization, right? So here is another question. How many kilojoules of energy are needed to change 20.0 grams of water at 20.0 degrees Celsius to steam at 100 degrees Celsius? So the way I would do this, and by the way, before I even do this problem, let me go back to the table I showed you before, because that table gives you the heat of vaporization of water. Let me see what it is. Okay, so according to the table, the heat of vaporization of water is 2259 joules per gram, all right? Okay, so just thought I should point that out to you. That is right here, okay? Now, go back to the question. So the question is asking for you to calculate the amount of heat to carry out this change. Now, here's the thing. We're going to start off with H2O liquid at 20.0 degrees Celsius, and you're warming it to H2O liquid at 100 degrees Celsius. In fact, 100.0 degrees Celsius. This is another Q is equal to M times C times delta T equation that you're going to need to calculate that heat. And then to go from this to H2O gas at 100.0 degrees Celsius, this is going to require the heat of vaporization. Heat of vaporization. Okay, so to calculate the first part here, Q is equal to the mass, which is 20.0 grams, times 4.184 joules, times the temperature change, which is 100.0 degrees Celsius, minus 20.0 degrees Celsius. And I'll work that out. In fact, let me put the answer here. So that's 100 minus 20, that's 80 times 4.184 times 20. So I'll round this off to 3 sig figs, which would be 6690 joules. And then to calculate the other part, heat of vaporization part, the heat required in that case would be equal to the mass, which is 20.0 grams, multiplied by the heat of fusion, which, as I said before, is 2259 2259 joules per gram. So 2259 times 20, and that gives you 4518. 4518. In fact, I'm sorry, 452, because we have to round off to 3 sig figs 00 joules. And all we have to do to find the total heat is to add these two together. So that's 45200 joules plus 6690 joules, and according to my calculation, this works out to be equal to 51900 joules. And I think I forgot to do this part in the previous question, and that is to convert the joules to kilojoules, but by now you all should know how to do that. So that's 1000 joules here, 1 kilojoules here, and when you work that out, that works out to be equal to 51.9 kilojoules. All right, I think I should have done that also for the previous problem, but I didn't. But of course, by now you guys should know how to do that. Okay, I'm going to stop this video at this juncture, and I'm going to start with a discussion of the hydrogen bond in the next video. All right, so until next time.